We're going to use some slightly smaller numbers here to walk through an example without using the EIGRP topology table. And the great thing is the theory is the same. It all works the same. It's just you may be dealing with bigger numbers on an exam question, and you definitely will be working with bigger numbers on production equipment, as we've already seen. So we're assuming a 3 successor route and 3 possible feasible successors, and that's really hard to say, so I'm only going to say it once. The successor has an FD of 5 and an RD of 4. Our first FS, possible FS, has an FD of 9 and an RD of 7. Number 2 has an FD of 8 and an RD of 6. Number 3 has an FD of 6 and an RD of 4. All we need to do is apply the feasible successor condition. Sounds complicated, but all we're doing is saying, is the RD of the possible FS larger than the FD of the successor? If it is, then it's out. And here, routes 1 and 2, definitely 7 and 6 are definitely both higher than 5. And what EIGRP is doing here, it's being, and here's that word again, I'm going to use it again, it's being proactive about routing loops. It really is. It's looking at these and saying, okay, why, if this particular route's so good, like say possible feasible successor number 1, if this route's so good, why is the next top metric for that route higher than the entire path metric of the route I've already named as the successor? And it can't authoritatively prove there's a routing loop, but it raises suspicions. So EIGRP just looks at it and says, hey, there's a possible routing loop there. I'm not even fooling with it. But as long as the reported distance of the possible FS is lower than that of the FD of the successor, then EIGRP says, you know what, you're not so bad. You can come in. We'll put you in the topology table. So this is all about avoiding routing loops. Now, we're going to take another look at feasible distance and reported distance and the condition in action. And you really have to watch these values, as I mentioned. But here's the diagram. You might want to pause the video and jot this one down. Router 1 has 3 potential paths to router 3. And the feasible distances and reported distances for the paths from RD's point of view are, and they're there on the board, and you see the different numbers, the metrics I've got on each path. Now we would look at these and say, okay, is each route, is it going to be a successor, a feasible successor, or neither? Well, R1 is going to put the path through R4 into its routing table because it has the lowest feasible distance. So that is our successor, and it would be put into the topology table. Now the router is going to consider, should I put these other 2 paths in my topology table as a feasible successor? Well, let's look at those and see what happens, because the one through R1, R2, and R3, we see that has an overall feasible distance of 70 because we have a 50 and a 20, so we've got 70. The reported distance of that route, which is the next hop routers metric, is 20 because the cost for the path from R2 to R3 is 20. So there we have an RD of 20. The successor route has an FD of 40, so therefore this is a feasible successor. Bit of a red flag on practice exam questions and possibly on real exam questions. Anytime you got a larger metric here, you want to watch that one, because here's why. We have an FD of 115 for the path 153. We got a 40 and a 75. We add those up. But the reported distance is 75. And that is much higher than the feasible distance of the successor, so this would not be a feasible successor. So from top to bottom there, the route from 143, that's our successor, 123 is a feasible successor, and 153 is not even going to be found in the topology table. That's all you have to do. It doesn't matter if the drawing gets bigger, and someone gives you 4 links or 5 links between the routers. Just add the numbers up, watch your next top metrics, and you'll nail the question. No question about it. Now, what happens, though, if you don't have a feasible successor? Well, it's not good, but we do have a process for that. We love the fact that EIGRP calculates those backup routes before we need them. We love that. That's redundancy at its finest. But what if we go for that backup route and we don't have one? Well, if a successor route is lost and there is no feasible successor, the router will take 2 actions. First off, the route is put into active state, and I believe I mentioned way earlier in this course, or as a matter of fact I know I did, that active is almost always good, and I was going to tell you one time where active was not good. This is it. The route is put into active state. In EIGRP, what that means is the route is currently being calculated and we can't use it. Now, if you're fortunate and things go the way they should, it's going to be in active state so fast that you won't even see the A next to it when you run show IP EIGRP topology. Because let's go back just a little bit here. See that P right there? I'll give you an extra little bonus lesson here. This is from the topology table. The letter P there means passive. That means the route is not currently being calculated and it can be used. So this is one time when passive is better than active, because again, the P for passive means we can use the route. A for active means it's currently being calculated and you can't, EIGRP can't use it. Now, if things go smoothly, the route stays inactive for such a little amount of time that you can go a long time without even seeing the letter A here, because it's just that fast. If it stays inactive, it's what we call SIA, stuck inactive, and that's a topic for another day because that is a tough nut to crack at times. But that's the difference there between the P and the A and the topology table. Now, what else happens? The router sends dual query packets to EIGRP neighbors asking them if they have a loop-free path to the destination in question. Dual is our routing protocol algorithm for EIGRP. So the dual query goes out to the neighbors. Basically, and they ask two friends, and they ask two friends, and the neighbor is going to answer that query with a reply packet, letting the querying router know about the valid path if they had one to send. Now, if the queried neighbors don't have a path to that network, then they ask two friends, they ask all their neighbors, and they ask two friends, and the query process just continues until somebody says, hey, I've got a path to that network, or no router can do so, and the query process finally ends. Now, EIGRP's major advantage over RIP. RIP's pretty much gone from the CCNA example. We're going to talk about it a little bit here. Both support VLSM, so why not RIP2 over EIGRP? Well, here's why. If you or I were asked what the optimal paths were here between 1 and 2, routers 1 and 2, we wouldn't hesitate because we'd look at this and say, okay, this is T1 speed all the way around here through 3 and 4, and then 1672, that's all T1. But what about this, 152? Well, that's 56K. That's a lot slower than a T1 line. This is a problem with RIP, though, because RIP is going to look at that and just count hippity hops, as I say somewhat derisively, actually very derisively, because RIP is not even looking at the speed of the path. It's just saying 1 hop, 2 hops. Oh, well, 2 hops is better than 3 hops, so we're going this way. This is why you don't see a lot of RIP version 2 and why you see a lot more of EIGRP. So let's see. I believe that we are at the point of configuring EIGRP. We're going to head into our lab work next. We're going to start with a very basic fundamental configuration. Of course, we're going to mess with it from there, right? Routers 1, 2, and 3 are going to be in EIGRP AS100. We're going to build that over our already existing frame relay network, and we are going to add as we go along and then start looking at some of these tables on live equipment. So take a breather. I'll see you on the next video, and we'll jump into our lab work.